I am Lavanya Jayaraman from Department of Computer Science Engineering, Sri Venkateshwara College of Engineering. In this video, we are going to see CS22032 Deep Neural Networks, Unit 5 Recurrent Neural Networks. So, what is recurrent neural network? Recurrent neural networks are a special type of artificial neural networks designed to process sequential and time-dependent data. Unlike traditional feed-forward networks, RNN use feedback connections that allow information to persist across time steps. This enables them to remember past input and use that context to make better predictions. So let's get started about the detailed view of recurrent neural networks. So first, sequence data. So what is sequence data? It refers to data where the other observations matters. Unlike static or independent data points, sequence data has a natural structure where each element is connected to previous and sometimes future elements. Because of this, the meaning of one data point often depends on its context within the sequence. This creates a key characteristic, dependency over time or position. So, in sequence data, information is not isolated. Instead, it evolves step by step, and each step carries meaning influenced by what came before it. So, that is why handling sequence data requires special models that can capture context and memory. The real world examples here are one of the most common example is text data such as sentence, paragraphs and documents. So in natural language, words are not independent. The meaning of a word depends heavily on surrounding words. For example, the word bank can mean a financial institution or the side of a river. And only context tells us the correct meaning. So this is why sequence understanding is crucial in language processing. Another important example is speech signals. So speech signal is a continuous stream of sound over time. Each sound wave is connected to previous one and meaning is formed through patterns across time. If we break speech into independent parts, we lose important information like tone, rhythm, and pronunciations. We also have a time series data which is widely used in industries like finance, weather forecasting, and IoT systems. So in time series data, values are recorded at regular time intervals. For example, temperature readings change over time and each value is influenced by past trends and seasonal patterns. Similarly, sensor data from machines helps to predict future behavior based on past performance. Another critical example is biomedical signals such as EEG and ECG. These signals represent brain activity and heart activity over time. They are highly sequential in nature, where even small changes in the pattern can indicate important health conditions. So, understanding the sequence is essential for accurate diagnosis. So, finally, stock prices. So these are classic example of sequence data in finance. The price of the stock is at any moment is influenced by historical trends, and market sentiment and recent movements are also under the value of sequence manner. So traders and prediction models rely highly on past sequence to estimate the future behavior. Sequence data is everywhere around us actually. So it represents information that unfolds over time or order, where context is not optional. So it is essential one. So understanding this dependency is the foundation for building models that can work with real world temporal and contextual data effectively and more efficiently. Sequence models and sequence data. So, what are sequence models? Sequence models are a class of machine learning and deep learning model that are specifically designed to work with ordered data where the arrangement of inputs is not random but meaningful. Unlike traditional models that assume each input is independent, sequence models recognize that data points are connected across time or position. The most important idea in sequence models is that the output is not determined only by the current input. Instead, it depends on two key components: current input and previous or past input in the sequence. This means the model maintains some form of memory or context, allowing it to understand how earlier information influences the present. Because of this ability, sequence models are extremely powerful in tasks where temporal relationships or contextual dependencies are important. So, whenever the meaning of data depends on what came before it, sequence models are required. So, let's move on to sequential data. Sequential data refers to any type of data where order matters and where each element in the data sequence is connected to the previous element. In such data, changing the order of elements can completely change the meaning or interpretation of the information. So, a key property of sequential data is dependency across elements. This means each data point is not independent but is influenced by earlier points in the sequence. So, in some cases, it may also depend on future context depending on the type of model being used. In sentences or a natural language, words are arranged in a specific order to form a meaning. For example, the sentence, if it is I am learning deep learning, means it makes sense only because the words are in the correct sequence. If we rearrange the words randomly, the meaning is lost. So each word depends on the previous words to define its role and meaning. So in speech, the information is not stored as isolated sound values. Instead, speech is a continuous waveform where each sound is connected smoothly to the next. The pronunciation of a word depends on the sequence of data and stress patterns and timing. Without considering sequence, speech would become meaningless noise. So, in time series data such as temperature readings, stock market prices, or sensor outputs, each value is recorded over time. The value at any given moment is influenced by past trends, seasonal patterns, and gradual changes. For example, stock prices cannot be understood by looking at a single day. They require analysis of the entire sequence of past prices. So, to summarize in a deeper sense, sequence models are designed to learn context, memory, and dependency over time. While sequential data is any form of data where order and history are essential for interpretations. So, understanding these concepts are the foundation for advanced models like RNN, LSTM, GRU, and transformers, which are all built to handle the sequential information effectively. Types of sequence models. These models are categorized based on how inputs and outputs are structured in a sequence. The first type is one-to-one. So in one-to-one model, we have a single input and a single output. This is the simplest form of neural network where there is no sequential dependency involved. So for example, image classification is a one-to-one mapping where one image produces one label as the output. Next is one to many. So in one-to-many model, we start with a single input, but the output is a sequence of multiple values. This means one input generates a sequence over time. So a good example is image captioning, where one image is used to generate a sentence describing it word by word. So next one is many to one. So in this case, we have a sequence of inputs, but the model produces a single output. Here, the model analyzes the entire sequence before making a decision. A common example is sentiment analysis, where full sentence or paragraph is processed to predict a single sentiment label such as positive or negative. Next one is many to many. In many to many models, both input and output are sequences. This means the model processes a sequence and produces another sequence as input. A typical example is machine translation, where a sentence in one language is converted into a sentence in another language. Another example is video labeling or speech recognition, where each input element is corresponds to an output element over time. So sequence models can take different forms depending on the relationship between input and output, where it is one input, many inputs, one output, or many outputs. So these types helps us to choose the right model architecture for different real world sequential problems. So let's we discuss deeply into the sequence models, one to one and one to many. In one to one, as we already shown in the previous slide, as a simplest type of a model, where we have the single input and a single output. So this means the model takes one data point as input and produces one corresponding output. There is no sequence involved in either the input or the output. So this is not a true sequence model, but it is often used as a baseline in deep learning systems. So a common example of one-to-one model is image classification. So in this case, the model takes an image as an input and produces a single label as output, such as cat, dog, or car. Each input is treated independently and there is no dependency on previous inputs. Because of this, its simplicity, this type of model is often used as a starting point before moving to more complex sequential architectures. Then next one is one to many model. In one to many model, we have one single input that generates multiple outputs forming a sequence. This means the model takes one input and then produces a series of outputs step by step. Each output is generated based on the input and the previously generated outputs. So a well-known example of this is image captioning. In image captioning, the model takes a single image as an input and generates a full sentence describing the image. The output is not just a one word, it is a sequence of words that together form a meaningful description. For example, given a image of dog playing in a park, the model might generate the sentence, um, a dog is playing in a green park. Here, each word is produced one after another, forming a complete sequence. So, one-to-one model map a single input to a single output, while one-to-many model takes one input and generate a sequence of outputs over time. So, hope you all understand about these two models. In Next one is many to one. So in this model, we have a multiple inputs but a single output. So this means the model takes an entire sequence of data as input and processes it step by step. Instead of producing an output at each step, it waits until it has seen the full sequence. Then it summarizes the entire sequence into one final output. This type of model is very useful when we need to understand the overall meaning or pattern of a sequence. A common example is sentiment analysis. In sentiment analysis, the input is a full sentence or paragraph, which is a sequence of words. The model reads the entire text and then produces a single output such as positive, negative or neutral sentiment. So here the whole sequence is compressed into one meaningful prediction. Many to many model. We have input sequence and an output sequence. We have sequence. So the model reads the input sequence of inputs and generates the corresponding sequence of outputs. uh, we have many inputs and then many outputs in this case. So this means both input and output are sequential in nature. So a classic example for this is language translation. So when translating a sequence from English to French, the model takes an English sentence as input and produces a French sentence as output. Each word or token in the input contributes to generating the output sequence. So the input and output sequences may or may not have the same length depending on the task and language structure. Some translations may be shorter while others may be longer. So another example includes tasks like a sequence labeling or a speech to text, where each input element is mapped to an output element over time. So many to one model compress an entire sequence into a single output, while many to many model transform one sequence into another sequence, either of the same or different length. These models are fundamental in handling the real-world sequential tasks like text processing, translations, and speech recognitions. Recurrent neural network. So these are a special class of deep learning models designed specifically for sequential and time dependent data. So unlike standard neural networks that treat every input independently, RNN are built to understand that data often comes in an ordered form where each element is connected to what came before it. So the most important idea behind RNN is memory. Instead of processing each input in isolation, RNN maintain information from previous steps so that they can use past context while processing the current input. This ability allows them to capture temporal dependencies, meaning relationships that unfold over time or sequence positions. To achieve this, RNN use a mechanism called a hidden state. The hidden state can be thought of as the network's internal memory. At each time, the model takes the current input and combines it with previous hidden state. This updated hidden state is then passed forward to the next step in the sequence. So this creates a chain-like flow of information through time where each step is influenced by everything that came before it. This is what gives RNNs their recurrent nature. Recurrent or recurrent nature. So mathematically and structurally this is implemented using a loop or feedback connection. So unlike feed forward networks such as ANN or CNN where information moves strictly in one direction, RNN allow information to cycle through the network. This loop enables the model to remember earlier inputs while processing the new ones. So now let's compare this with the traditional neural network to understand why RNN are necessary. So in traditional feed-forward network, inputs are assumed to be independent and unrelated. Each input is processed on its own without any memory of previous inputs. This works well for problems like image classification, where each image is separate and does not depend on other images. So, however, many real-world problems do not follow this independent structure. Instead, they are inherently sequential. For example, in NLP, the meaning of word depends heavily on the words that come before it. So, a word like bank can mean different things depending on the sentence context. Similarly, in time series data such as stock market prices, weather data or sensor readings, each value is influenced by previous values. A single data point alone does not provide enough information to make accurate predictions. So in speech processing, the meaning of a sound depends on previous sounds, rhythms and pronunciation flow. Without sequence awareness, the model would lose important contextual information. So, RNN addresses all these challenges by maintaining a continuous flow of information through their hidden states. This allows them to remember past information, process current input, and make informed predictions based on both. So, recurrent neural networks are powerful deep learning model designed to process sequential data by maintaining memory through hidden states. They use a feedback connection to capture temporal dependencies, making them highly effective for tasks like language modeling, speech recognition, and time series for forecasting. So, the fundamental building blocks of RNN. The basic unit of a RNN is called the recurrent unit. This unit is responsible for handling sequential information step by step. Unlike a normal neural network unit that processes input only once, a recurrent unit processes data over time, making it suitable for sequential tasks. The most important concept inside this recurrent unit is the hidden state. So the hidden state acts like a form of memory for the network. It stores information about what has been seen in previous time step and carries that information forward as the sequence progresses. So at each time step, the hidden state is updated using two sources of information. First, the current input, and second, the previous hidden state. By combining these two, the network is able to understand both the present input and its historical context. This creates a feedback mechanism where information flows not only forward but also cycles through time. Because of this feedback loop, the network can learn patterns that depend on sequences such as trends, contexts, and temporal relationship. This ability to remember and update information over time allows RNN to learn from past input and use that knowledge to improve current and future predictions. Because of this powerful sequential learning capability, RNN have been successfully applied in many real-world tasks. For example, in unsegmented and connected handwriting recognition, RNN can understand continuous handwriting where individual characters are not clearly separated. So in speech recognition, they help to convert spoken language into text by analyzing sound sequence over time. So, and in NLP, RNN are used for tasks like language modeling, text generation, and sentiment analysis, where understanding word order is essential. So they are also widely used in neural machine learning, where a sentence in one language is converted to another language by processing and generating sequence. So the recurrent unit with its hidden state and feedback mechanism is what gives RNN their ability to understand the sequential data and makes them powerful for a wide range of real world applications. So this diagram illustrating the neurons with recurrence, which forms the basic of recurrent neural networks or RNN. So on the left side, we see a single recurrent cell. This cell takes two inputs. The current input vector denoted as x sub t and a hidden state h sub t, which represents information carried over the previous steps. So the key idea here is that the network does not just process inputs independently. It remembers past information. Now on the right side, the diagram shows this same recurrent cell unrolled across time. At each time step, t equals 0, 1, 2 and so on. The network receives a new input like x0, x1 and x2. Each of these inputs is processed along with the hidden state from the previous step. For example, the hidden state H0 is passed to the next step to help to compute H1 and so on. This creates a chain-like structure where information flows forward through time. At each step, the model produces an output shown as y hat 0, y hat 1 and y hat 2. The equation at the bottom summarizes this process. Y hat sub t equals a function x sub t and h sub t minus 1. So the output at time t depends on the current input and the previous memory. This ability to retain and use past information makes RNNs especially useful for sequential data such as text, speech or time series data. So recurrent neurons allow neural networks to have a form of memory, enabling them to model patterns that evolve over time. The output of a recurrent neural network depends on two key things. First, the current input, which we denote x sub t. Second, the previous memory, also known as the hidden state, denoted as h sub t minus 1. So these two components are combined to produce the new hidden state. Mathematically, we write this as h sub t equals f of x sub t and h sub t minus 1. So in simple terms, this means the model updates its memory at each step by using both the new input and what it has learned from the past. Let's understand the standard RNN, standard recurrent neural network. So a standard RNN can be viewed as a model specifically designed to process data that comes in a sequence where each step depends on the previous ones. To fully understand how it works, we break it into two important ideas, configuration and architecture. So let's start with the configuration. Configuration of RNN refers to how multiple recurrent units are arranged and connected in a full model pipeline. In real-world applications, we rarely use just a single RNN cell. Instead, we often stack multiple RNN layers or connect them in different patterns depending on the complexity of the task. For example, in some systems, one RNN layer processes the input sequence and passes its output to another RNN layer for a deeper understanding. This entire flow of information through multiple RNN components is what we refer to as the configuration of the model. It defines how data moves through the network across time and across layers. So now moving to the second part, architecture. Second part is architecture. So the architecture refers to the internal structure of the single recurrent unit. So this is where the actual computation happens at each time step. A key point to understand is that not all RNN architectures are the same. The simplest form is the vanilla RNN, where there are also more advanced architectures like LSTM. LSTM is nothing but long short-term memory, and GRU gated recurrent unit, which are specifically designed to handle long-term dependencies and overcome limitations of basic RNN. Even though these variants differ internally, they all follow the same core idea. Processing sequences step by step while maintaining a memory of past information. Um, Next, the mathematical representation of a standard RNN in a more conceptual way. We define the RNN as a function f theta xt, h3 to yt, ht plus 1. This equation may look compact, but it represents the entire working mechanism of an RNN. So at every time step t, the RNN receives an input vector xt. This input could be anything depending on the application. For example, in NLP, xt could represent a word embedding. In time series forecasting, it could be a numerical measurement like a temperature or a stock price. Along with this input, the RNN also receives the hidden state from the previous time step H3. This hidden state is extremely important because it acts as the memory of the network. It carries forward all relevant information from earlier time steps, allowing the model to maintain context over time. The RNN then processes both XT and HT together. It combines current information with past memory to produce two outputs. First, it produces YT, which is the output at time step T. This could be a prediction such as the next word in a sequence, a classification label, or a numerical forecast. Second, it produces the updated hidden state ht plus 1, which will be passed to the next time step. This updated hidden state now contains a refined version of the model's memory, incorporating both past and current information. The learnable parameters of the model are represented by theta. These include all the weights and biases that the model adjusts during training. Though backpropagation through time, the RNN learns how to update these parameters so that it can be better capture patterns in the sequence data. The most important idea here is the recurrence mechanism. Unlike feed-forward network where information flows only in one direction, RNN create a loop over time. This loop allows information to persist across steps, enabling the network to learn dependencies that span across long sequence. So at every single time step, the same process repeats. The model reads inputs, combines it with memory, produces output, and updates its memory for the next step. So a standard RNN is a powerful sequence model that processes data step by step using a shared function across time. It maintains a hidden state as memory, allowing it to capture temporal relationships and learn patterns across sequences in a structured and continuous manner. Stacked RNN. So it is also called as a deep RNN. It is a neural network architecture where multiple RNN layers are placed on top of each other. Instead of using just one recurrent layer, we stack several layers so that all the model can learn more complex and abstract patterns in sequential data. The key idea here is simple but powerful. The output of one RNN layer becomes the input to the next RNN layer. This allows the network to learn representations at different levels of abstraction. Lower layers capture simple patterns while higher layers captures more complex temporal structures. Layer-wise understanding. So first layer 1. So in the first layer we receive the original input sequence which we can denote as x of x of 0 comma t, which means x base 0 comma t. So this layer has its own hidden state represented as h1 t and its own set of parameters theta 1. The function for this layer can be written as f theta 1 belongs to x naught of t bar h1 comma t belongs to x1 t bar h1 t plus 1. Here the important idea is that first RNN layer processes the raw input and produces a transformed sequence h of 1 comma t, which is then passed to the next layer. So layer 2. Now the second layer takes the output of the first layer as its input. So it has its own hidden state h of 2 comma t and its own parameters theta 2. The function becomes f theta 2 equal to f theta 2 x1 1 comma t comma h2 comma t belongs to x2 comma t and h2t plus 1. So in this stage, the model is no longer working with raw input. Instead, it is working with more refined representation learned by the previous layer. So this allows it to capture deeper sequential patterns. So next one is layer 3. So similarly for the third layer and beyond, the same pattern continues. Each layer has its own hidden state hn comma t and parameter theta n, and it processes the output of the previous layer. The function f of theta n x n minus 1 t and hidden h n comma t, which gives x of n t h of n comma t plus 1. This shows that every layer in the stack works independently in terms of parameters, but they are connected through the flow of data. So the general representation is for any layer I, we can write f theta I x of x I minus 1 comma theta bar h I comma t, which gives x I t bar h I t plus 1. This equation captures the essence of stacked RNN. So a single RNN layer can capture basic sequential dependencies, but it may struggle with complex patterns in real world data. So by stacking multiple layers, the model becomes deeper and more powerful. Each layer learns a different level of understanding. Lower layers focuses on simple short-term patterns and higher layers capture more abstract long-term dependencies. This hierarchical learning structure allows stacked RNN to perform better in complex tasks like language modeling, speech recognition, and machine translations. So in a stacked or multi-layer RNN, each layer function has an independent recurrent neural network. This means that every layer has its own hidden states and processes the sequence over time separately. So however, these layers are connected vertically The key idea is that the output sequence from one layer becomes the input sequence to the next layer. So instead of feeding raw input directly to the into every layer, we pass learned representations upward through the network. So mathematically, we can express this flow as um, x0 comma t uh, belongs so gives x1 t and then it sends the data to x2 t till xn of t. So here x sub 0 comma t represents the original input at time step t, while x sub 1 comma t, uh, x sub 2 comma t and so on, which represents the transformed outputs at each successive layers. So x1t is the output for x0t and x2t is the output for x1t. So let's move on to the next step further and understand this diagram, which represents a stacked or multi-layer recurrent neural network. Unlike a simple RNN that has only one layer, this model consists of multiple RNN layers stacked on top of each other. So overall structure is given here. At the bottom we have layer 0 and above it we have layer 1. Each layer contains its own sequence of RNN cells processing the input across time steps. The key idea here is that each layer learns a different level of representation. Input to the first layer. So let's start with layer 0, the layer 1. At each time step, it receives the input sequence shown here as x0, x1 and so on. These inputs are fed into the RNN cells one step at a time. Within this layer, information flows horizontally across time from one cell to next through hidden states like H00, H01 and H0T. This allows the model to capture temporal dependencies in the input sequence, passing information upward, uh, which instead of producing the final output directly, layer 0 passes its hidden states upwards to the next layer, layer 1. So the output at each time step from layer 0 becomes the input to layer 1. For example, H00 is passed up as input to the first cell in layer 1 and H01 is passed to the next cell. Processing in the second layer, in layer 1 the process repeats. Each RNN cell now takes two inputs, the hidden state from the previous time step in the same layer and the output from the lower layer at the same time step. This layer can now learn higher level patterns since it builds on the features extracted by layer 0. Again, information flows horizontally through hidden states like H10, H11 and so on. Final outputs. So at the top, the hidden states from the final layer such as H10 and H11 can be used as the final output of the network. These outputs are richer and more abstract because they have passed through multiple layers of processing. So what's the benefit of stacking RNN layers? A single layer RNN captures basic temporal patterns, but the multi-layer RNN can capture more complex and hierarchical patterns. So you can think of it like this. The first layer learns simple features and the second layer learns more abstract patterns built on top of those features. Next topic is bidirectional RNN. So shortly we will write as BI or NN. So a bidirectional RNN is designed to improve sequence understanding by processing data in both directions. Unlike a standard RNN, which only reads the sequence from left to right, a bidirectional RNN uses two separate RNN to capture more content. So the first RNN processes the sequence in the forward direction, meaning from left to right. This is similar to how we naturally read text in many languages. The second RNN processes the same sequence in the reverse direction from right to left. This allows the model to also consider future context while making decisions. By combining both directions, the model gains a much richer understanding of the sequence because each element is interpreted using both past and future information. First one, forward RNN. So left to right. So let's first look at the forward RNN. In this direction, the model processes the sequence step by step from the beginning to the end. At each time step, the RNN takes an input X and the previous hidden state HT and produces an output and an updated hidden state. This process can be written as f theta of x naught comma y naught equal to y naught comma h1 and f naught x1 comma h1 equal to y1 comma h2 and up to f theta xt comma ht equal to yt yt comma ht plus 1. So here HT represents the hidden state which carries memory forward through time. Theta represents the shared parameters of the forward RNN. YT represents the output at each time step. So the key idea is that the forward RNN builds understanding based only on past information. Okay. So why forward RNN alone is limited? So forward RNN only sees what has already happened in the sequence. It does not know what comes next. So in many tasks that is not enough because context often depends on future words or future time steps. For example, in a sentence, the meaning of word can depend on words that appear later. So the forward RNN gives us a left to right understanding of the sequence. In the next step of by RNN, the backward RNN will complement this by processing the sequence in reverse, which allows the model to combine both past and future context for better prediction. So second one, backward RNN and output combinations. So backward RNN, so right to left. So the sequence is processed in opposite direction from right to left. This means the model starts from the end of the sequence and moves backward towards the beginning. This is important because it allows the network to access future context which the forward RNN cannot see. So in this case, we define a separate hidden state for the backward pass, which is represented as h bar t, and a separated set of parameters theta. These parameters are independent from the forward RNN, meaning the backward model learns its own representation of the sequence. The backward recurrence can be written as f theta xn h bar n equal to y bar n h bar n minus 1 and f theta bar of n minus 1 h n minus 1 equal to y bar of n minus 1 h bar of n minus 2. So it goes up to f theta of f theta bar xt comma h t bar equal to y t bar h t bar t minus 1 bar. Here ht bar is the hidden state of the backward RNN. Theta bar represents its parameters and yt bar is the output at each time step in the backward direction. So while the forward RNN learns from past to future, the backward RNN learns from future to past. So next one is output combination, or also called as concatenation. So the most important part is combining the both direction. So at each time step we now have two outputs, forward output and then backward output. So forward output here represented as yt and the backward output here is represented as y bar t. These two outputs are combined together usually by concatenation to form a richer representation. So, the final output sequence becomes y0, y0 bar, y1, y1 bar up to yn, yn bar. So, this means that for every time step, the model now has information from both directions. Okay, so the key advantage of bidirectional RNN is that each time step is no longer dependent only on past information. Instead, it has access to past context from the forward RNN and then future context from the backward RNN. So this combination gives the model a complete understanding of the sequence. For example, in natural language, understanding a word often depends on both the words before it and the words after it. Similarly, in speech or biological sequences, context on both sides is important for accurate interpretations. So here is the architecture of a bidirectional RNN. So there are two layers, forward layer and a reverse layer. In standard RNN, the model processes the sequence in a single direction. So this means it uses only past information to make predictions across the current state. However, in a bidirectional recurrent neural network, the processing happens in both directions. It considers past information from previous steps and future information from upcoming time steps. By combining both bi-RNN, which provides a better understanding of the entire sequence context, leading to more accurate predictions. So this makes bi-RNN especially useful in tasks like language understanding, speech recognition and text classification, where context from both sides of a sequence is important. So here is the example for bidirectional RNN. So stacked bidirectional RNN and a real model. So understanding the context with bank, consider the sentence, the bank is near the river. This sentence is a great example of why bidirectional RNN are important. The word bank is ambiguous, so it can have multiple meaning. It could refer to a financial institution or it could refer to the side of a river. So now let's see how a bidirectional RNN helps to resolve this ambiguity. So first, forward RNN, left to right. So the forward RNN reads the sentence from left to right. The bank is near the river. So it will split the words. So at the point it processes the word bank, it only knows the words that came before it. So it it understands context like the bank, but it does not yet know what comes later in the sentence. So based only on past context, the meaning of bank is still uncertain. So second, backward RNN. So right to left. Now the backward RNN reads the sentence in reverse. So in reverse means how it comes? River, the, near, is, bank, the. So when it processes the word bank, it already knows that later in the sentence there is the word river. So this future context strongly suggests that bank refers to the river bank, not a financial institution. So next one is combined understanding. So when we combine both directions, the forward RNN produces past context, the backward RNN provides future context. So together the model gets a complete contextual understanding, allowing it to correctly interpret ambiguous words like bank based on the full sentence. So stacked bidirectional RNN is formed under when multiple bidirectional RNN layers are placed on the top of each layer. So this means the output is one bi-RNN layer becomes the output of the one bi-RNN layer becomes the input to the next bi-RNN layer. So each layer learns increasingly complex representations of the sequence. So the lower layers captures basic patterns while higher layers captures deeper semantic and contextual meanings. So this stacking leads to much richer and more powerful representation of sequential data. Real model example, Elmo 2000 in 2018, a well-known real-world example of bidirectional RNN. So it uses stacked bidirectional LSTM as its core architecture. Character level input representation, meaning it processes text at the character level instead of just words. From this, it generates context-aware word embeddings where the meaning of a word changes depending on the sentence it appears in. For example, for the same example, the word bank will have different embeddings depending on whether it appears in a financial context or a river context.